Chapter 3 discusses numerical descriptions of data. Chapter 3 is an important chapter, a key chapter that you need to be very meticulous as you work through, and to be sure that you're comfortable before you move on, because much of what we'll do later on builds upon material in Chapter 3. Section 3.1 starts out with measures of the center, what's commonly referred to as measures of central tendency, where it gives us three primary measures of a data set, looking at their center value, the mean, the median, and the mode. The arithmetic mean, as it's often called, is simply just the average of the data set. Also recall that we're potentially talking about two different types of calculations if we're dealing with populations or with samples. A population is the entire data set cumulatively, so all possible values within the data set are collected and analyzed, whereas a sample is a selected portion of the data set that we're going to use. And that example would be if we're wanting to figure out median U.S. income of households, well, the population would be all households, which constitutes hundreds of millions of households. It would be feasibly impossible for us to contact and gather data on millions, hundreds of millions of households to find their income data. So to save time and money, we simply select a random sample of the population that may include only perhaps a few hundred or even maybe at most 1,000 households out of those hundreds of millions. And if it is a representative random sample, then that sample data will give us accurate results where we don't need the population. But nevertheless, for the mean, we can look at population mean versus sample mean. Population mean is referred to as mu. This is the Greek letter mu, and it's simply going to be the summation of all of the data values within the population divided by n. And in our formula, n there is a capital N, and capital N denotes all values within the population. The sample mean is referred to as x bar, so an x with a bar over it, and x bar is simply the summation of all data values within the sample divided by n, but now we have a lowercase n, and the lowercase n represents the data values within the sample only. So we have the population mean, mu, the sample mean, x bar, and those are used extensively throughout the course. The median value is the second central tendency, and it's simply just the middle value. And that's very easy to oftentimes look at and calculate. Whatever the middle value of the data set is, then that's going to be the median. If the data set has an even number of values, then the median is going to be the average of the two middle values. If we have an odd number within the data set, then it's simply just that unique middle value. The mode is the third central tendency measure, and it's simply the most frequent value within the data set. And it is possible to have no mode, a single mode, or data sets can be bimodal, where there may be multiple modes. So those are the three measures of central tendency that measure the center of the data. They should be relatively easy to calculate. Section 3.2 gets us into measures of dispersion, which is measuring the spread of the data. So we want to measure the center of the data, central tendency, and also the spread of the data. One key value that we calculate is the range. The range is simply the maximum value in the data set minus the minimum value of the data set. That's known as the range. The variance is extremely important and unique, and the variance is simply the spread of the data. So we also want to know how spread out the data is completely as it relates back to the mean value. And again, we're going to have a population variance versus a sample variance, depending upon whether we use population data or sample data. The population variance is known as sigma, so the Greek letter sigma, and you'll see these symbols within the text. Sigma squared is the variance, and then that formula is actually the summation of all data values, which are referred to as x. So the summation of xi, all data values, minus the mean, population mean mu squared, then divided by n, capital N, because it is the population we're dealing with. So sigma squared is the summation of all data values xi minus mu squared divided by n, whereas the sample variance is s squared, which is the summation of xi minus x bar, now the sample mean, squared, divided by n minus 1. And that is important as we go through when you're calculating the sample variance. You do have to use a lowercase n, number of values in the sample, minus 1, to adjust out the variance for any sampling issues that we may have. And although this course is beyond the scope of this course, there are some very lengthy and interesting formulas that one can work through to prove that we need to n minus 1 in the denominator for our sample variance s squared. But the reason we want the variance is really to find the standard deviation. The standard deviation of the data set is how much the values or the data differ from the mean or are spread away from the mean on average. And the standard deviation population and sample values are simply just the square root of the variance values. So the population standard deviation is simply sigma, the square root of sigma squared. And the sample standard deviation is simply s, the square root of the sample variance. And that tells us the overall spread of the data set as it relates back to the mean, and it turns out that the sample and the population standard deviation are key statistics that we need when we're talking about normal distributions, the empirical rule in a few moments, Chebyshev's theorem, and some other things. But all through the course, the standard deviation is a key statistic. The book also mentions, I want you to be aware of the coefficient of variation, which compares the spreads of two different data sets. You also can calculate population coefficient of variation versus sample coefficient of variation. The population coefficient of variation is simply the population standard deviation sigma divided by the population mean mu times 100% to get it in percent terms. Whereas the sample coefficient of variation is S, the sample standard deviation divided by x bar, the sample mean times 100% to get it into a percentage. And this is just a comparison. You can calculate two separate ones then to compare the differing spreads of the data, standard deviation as compared to the mean. The empirical rule is also of key importance. The empirical rule only applies, though, to normal or bell-shaped distributions, and we'll have an entire chapter devoted to analyzing normal distributions as we go forward. Turns out that many data sets do take on a normal distribution, and we can do some unique things if we do have normal distributions. What the empirical rule shows us is that we know if the data is normally distributed, bell-shaped curve, that approximately 68% of the data will lie within one standard deviation of the mean. So typically you see it as 1s plus or minus x bar. So on both sides, upper and lower, one standard deviation above and below the mean should contain approximately 68% of the data within that data set. If you bump it up to two standard deviations, then we know that approximately 95% of the data values lie within two standard deviations above and below the mean. And if you bump it up to three standard deviations, then 99.7 or practically all of the values lie within that range, three standard deviations above and below the mean. But this only applies if the data is normally distributed or bell-shaped curved. Chebyshev's theorem is a more broad rule that applies to any data set that occurs. So for any data set, whether it's normal or not normal, we know that at least 75% of the data lies within 1 standard deviation above and below the mean. And for any data set, we also know that 88.9% of the data lies within 3 standard deviations above and below the mean. I may have misspoken there. For the 75%, it's 2 standard deviations above and below the mean. 88.9 is 3 standard deviations above and below the mean. So that's Chebyshev theorem as well. Section 3.3, the last part, focuses on percentiles, which is fairly easy to calculate. Percentiles are simply looking at what percent you rank within a data set. Quartiles are similar. You can look at Q1 as the first quartile, which means it's at the 25th percentile. Q2 is effectively the median, it's at the 50th percentile, and Q3 is at the 75th percentile. Those are important as we go forward and pretty easy to calculate. The 5-number summary is oftentimes used in statistics, and this is just analyzing the minimum value, the first quartile, the 25th percentile, the median value, Q2, which is the 50th percentile, Q3, the 75th percentile, and then the maximum value. And looking at those 5 pieces of data, we can get a good read on what the data set looks like. Another measure that's oftentimes looked at is what's called the interquartile range. The interquartile range is simply Q3 minus Q1, the 75th percentile minus the 25th percentile. Box plots are often used to be able to present the data of the 5-number summary. So it's a way of plotting out or graphing the 5-number summary that's pretty easy to do. And then the chapter ends up with standardization. Z-scores are standardizing scores. If you're standardizing population values, then the Z-value is simply X, which is the values within the data set, that particular value minus mu divided by sigma. And if you're looking at a sample, it's X, which is the value within the data set you're concerned with, minus X bar divided by S. And that then standardizes the data and relates it back to what we talked about earlier with the empirical rule. And if you look to the inside of your cover of your textbook, the inside cover A says standard normal distribution. And this gives you tables, A and B both, for the standard normal distribution curves. And if you look at that, then if you calculate Z-scores or Z-values, then this is the table that you look at to interpret what percentage of the data lies above or below those values. And the empirical rule of 68, 95, and 99.7 is also embedded within this standard normal table. If you look at 1 standard deviation above and below, you'll see it's 68. 2 standard deviations above and below, you'll see it's 95. 3 standard deviations above and below. If you look within the table, you'll see it's 99.7. So that gets us through Chapter 3. Chapter 3 is in fact an important chapter. You need to take time and diligence to work through it. See you in Chapter 4.